We already studied rigid rotation, that is the rotation of a rigid body about a fixed axis. Now we will discuss another type of rotation of objects where the axis of rotation is not fixed but free. As everyday experience shows, a rigid body that is not subjected to external forces or the net external force acting on it vanishes can revolve around certain non-fixed axes while the orientation of the axis of rotation does not change. Such axes are the so-called free axes of rotation, and when bodies rotate about, then we can talk about free rotation. For example, a coin, a plate, or a flat disk can be made to rotate permanently around its diameter as an axis. Skillful acrobats are also able to balance and spin plates or disks on the tip of a stick about the axis of symmetry of the plate. The vertical direction of free axes can be studied experimentally by suspending the body with different orientations from the vertical axle of the rotating motor. For example, we can demonstrate in the experiment that a flat cylinder in vertical position can rotate sustainably around the transverse axis A1 passing through its center of mass and the point of its suspension, that is the axis A1 is a free axis. For a faster rotation, the instabilities occurring in the process cause for the disk to flip to a horizontal position and spin about its vertical axis of symmetry A2, that is the axis A2 is also a free axis of rotation. For any perturbation causing a deviation of the disk rotating about the axis A2 from its horizontal position, the spinning disk will return to its horizontal position, which shows that the stability of the rotation about the symmetry axis of A2 as a free axis is greater than that of the rotation about the axis A1. The case of a tall cylinder is the opposite, where the rotation around the transverse axis A1 appears to be more stable. In the study of the moment of inertia in rigid rotation, we already saw that the axes A1 and A2 determined in this experiment are the principal axes of inertia of both the cylinders with respect to these axes passing through their centers of mass. The moment of inertia of the flat cylinder with respect to the axis of symmetry A1 is the greatest of the moments of inertia about all the central axes of a cylinder. Similarly, the moment of inertia of the tall cylinder with respect to the transverse axis A2 is the greatest of the moments of inertia about all the central axes of a cylinder. Hence, in both cases the free axis with the greatest stability is the one with the largest moment of inertia. When we studied the moment of inertia of rigid bodies about their axes of symmetry, we presented their formulae computed for different solids. We saw that the moment of inertia I1 of a cylinder with uniform density about the axis A1 is equal to 1/4 times the mass m of the cylinder times the square of its radius r, plus 1/12 times the mass m times the square of the height h of the cylinder. Similarly, the moment inertia I2 of a cylinder with respect to the axis A2 is given by 1/2 times the mass m of the cylinder times the square of its radius r. The rotation of a cylinder about the axes A1 and A2 has the same stability for the condition stating that the moments of inertia I1 and I2 are the same. If we substitute the expressions obtained for I1 and I2 into this condition, then we can write the equation stating that 1/12 times m times h squared is equal to 1/4 times m times r squared. This gives the relation stating that 1/3 times h squared is equal to r squared, and we conclude that if the height h of a cylinder is equal to the square root of 3 times its radius r, then its rotation will be stable about both the central axes A1 and A2. We can also apply this condition to identify a cylinder of uniform density as a flat cylinder or a long one, depending whether its height h is greater or less than the square root of 3 times its radius r. Experiments with a homogeneous rectangular body lead to similar results. We already determined the moment of inertia of a cuboid with length a, width b and height c with respect to its principal axes A, B and C passing through the center of mass of the body, where these axes are the axes of symmetry of the cuboid. The moment of inertia Ia with respect to the axis A is equal to 1/12 times the mass m of the cuboid, times the sum of b squared and c squared. Obviously the terms in the sum in the expression of the moment of inertia Ib with respect to the axis B are a squared and c squared, and the terms in the sum in the expression of the moment of inertia Ic with respect to the axis C are a squared and b squared. These formulae show that if the length is a is greater than the width b and the width b is greater than the height c, then the moment of inertia Ic is greater than the moment of inertia Ib, and the later is greater than the moment of inertia Ia. It can be demonstrated in the experiments with a cuboid rotating about the principal axes that the central axes A and C are free axes, and the rotation about the axis C with the largest moment of inertia Ic is more stable. On closer inspection, the axis B is also a free axis, but the rotation about it is unstable, that is, its realization is as difficult as, for example, setting a cone to the apex. The above can be ascertained in a simple experiment with a box of matches thrown in the air by spinning it properly. The flying box can rotate permanently about the axes A or C, but not about the axis B. Based on our knowledge on the rotation of objects about fixed axes, we can determine the laws related to free axes. If a rigid body of arbitrary shape and mass distribution rotates with a constant angular velocity omega about an axle supported by ball bearings fixing its vertical direction along the z-axis, then all the mass elements mi of the body are subjected to the centripetal force Fi'. This force is the external constraint force exerted on the mass elements by the ball bearings, and it is equal to minus the mass mi times the square of the angular velocity omega, times the distance vector di of the mass element mi pointing from the axis of rotation to the mass element. When we studied systems of forces applied on rigid bodies, we proved that these systems can be reduced to the net force of the system acting on the body and a force couple producing a given torque on the body. According to this theorem on the reduction of a system of forces, the constraint forces Fi' acting on the mass elements of the body can be combined into or replaced by a net force F' applied on the body and a force couple producing a torque τ' rotating the body. If both the net force F' and the torque τ' vanish, that is if the ball bearings do not exert either force or torque on the body or on the axis of rotation relative to the body, then the ball bearings can be removed, and the axis of rotation of the rigid body is a free axis. Let us discuss the consequences of the vanishing net force acting on a rotating rigid body and the vanishing torque produced by the forces that the ball bearings exert on the axle about which the body is rotating. If dc denotes the direction vector pointing from the axis of rotation to the center of mass c of the rigid body, then the acceleration a of the center of mass rotating with the angular velocity omega is equal to minus the square of the angular velocity omega, times the distance vector dc. The theorem for the motion of center of mass of mechanical systems tells us that the center of mass of a rigid body moves as if the total mass of the system were concentrated at the center of mass, and the net force of all the external forces acting on the system were applied there. Consequently, the net force F' acting on the body given by the mass m of the body times the acceleration a, is equal to minus the mass m times the square of the angular velocity omega, times the distance vector dc. If the net force F' exerted on the system rotating about a free axis vanishes, then the length of the distance vector dc must be equal to 0, that is the center of mass of the rigid body must be on the free axis of rotation. We can also examine the consequences of the vanishing net torque produced by the force couple arising from the reduction of forces applied on the body. Let us suppose that the center of mass c of the body is on the z-axis that is on the axis of rotation, and determine the net torque τ' of the torques τ' I produced by the forces F' I acting on the volume elements mi of the body with respect to the center of mass. The net torque τ' can be written as the sum of the cross product of the position vector Ri pointing from the center of mass c to the mass element mi, and the force Fi' exerted on the mass element from I equals 1 to the number of the mass elements n in the rigid body. As already seen, the force Fi' is equal to minus mi times omega squared times di, and the net torque is given by minus the square of the angular velocity omega, times the sum of the mass mi times the cross product of the position vector Ri and the distance vector di from I equals 1 to n. Let xi, yi and zi be the coordinates of the position vector Ri in the Cartesian coordinate system attached to the rotating body, that is where the coordinate system rotates with the angular velocity omega about the z-axis. In the case of the horizontal distance vector di pointing from the z-axis to the mass element mi, the z-coordinate vanishes for any mass element. Then we can write the components of the torque τ' as follows. Its x component is equal to omega squared times the sum of mi times yi times zi from I equals 1 to n. Its y component is given by minus omega squared times the sum of mi times zi times xi from I equals 1 to n, and the z component vanishes. As a result, for the vanishing net torque τ' the products of inertia of the body with respect to the z-axis must be equal to 0, that is both I sub yz given by the sum of mi times yi times zi from I equals 1 to n, and I sub xz given by the sum of mi times zi times xi from I equals 1 to n must vanish. When we studied the moments and products of inertia of a body in the principal axis system, we saw that the products of inertia of a rotating body vanish in the principal axis system of the body. That is, the condition of vanishing net torque holds if the z-axis of rotation is one of the principal axis of the body, which passes through the center of mass c of the body. It follows from these considerations and the law of action and reaction that a rigid body rotating about an axle chosen as the fixed z-axis with an angular velocity omega exerts the force minus F' and the torque minus τ' on the structure fixing the direction of the axle. Here minus F' is given by the mass m of the body times the angular velocity omega, times the distance vector dc pointing from the z-axis to the center of mass c of the body. Similarly, minus tau prime is equal to omega squared, times the sum of the mass mi times the cross product of the position vector ri of the mass element with respect to the center of mass c on the z-axis, and the distance vector di of the mass element pointing from the z-axis to the mass element. The directions of the net force and torque are constant with respect to the body, that is, they rotate with the body. In the case of fast rotation, the magnitudes of the force F' and the torque tau prime can be very large if the center of mass is not exactly on the axis of rotation, or if the products of inertia I sub yz and I sub zx do not vanish. The results derived from the experiments or deduced from the conditions of the vanishing net force and torque can be summarized as follows. A rigid body generally has three mutually perpendicular free axes, namely the three principal axes of inertia passing through the center of mass of the body, which was showed by Johann Andreas Segner, a German physicist in 1755, and applied by the Swiss polymath Leonhard Euler between 1758 and 1765 to derive his equations describing the rotation of rigid bodies. With regard to the instability of the free axes, we have found that the rotation is stable about the axes corresponding to the largest and the smallest moment of inertia of the body, whereas the rotation is unstable is about the third principal axis for which the moment of inertia has the middle value. The most stable axis for free rotation is the one with the largest moment of inertia. As already stated, the principal axes A, B, and C of a rotating body with respect to the axis of rotation determined by the angles alpha, beta, and gamma passing through the point O, are aligned with the axes of symmetry of the ellipsoid of inertia of the body with respect to the point O. In the special case, where the ellipsoid of inertia of a body with respect to its center of mass is a rotational ellipsoid, that is, for example, IA is equal to IB but they are not equal to IC, as in the case of a homogeneous cylinder, all other central axes of the body lying in the plane of the principal axes A and B are also free axes. If all the principal moments of inertia of the body are the same, as in the case of a homogeneous sphere or cube, then all the central axes of the body are free axes of rotation. We can also talk about free axes in the case of the rotation of non-rigid bodies. For example, in a somersault the transverse axis passing through the center of gravity of the jumper's body is a free axis, whereas the free axis of a spinning skater is the longitudinal axis of the skater's body. The jumper and the skater can significantly change their moments of inertia with respect to the free axis during rotation, so that the angular velocity of their rotation also changes according to the conservation of their angular momentum, stating that the product of the moment of inertia and the angular velocity of the bodies of the jumper and skater must be constant.